What if a nuclear submarine built to survive the crushing depths of the ocean was launched into the cold, airless vacuum of space? Its tough, pressured hull is designed for extreme conditions, but could it handle space travel? In this video, we'll explore the mind-bending idea of turning a submarine into a spaceship. At first glance, submarines and spaceships may seem to share some common traits. Both are built to withstand environments where human life is impossible without artificial support. However, the differences between the ocean and space are immense, especially when it comes to pressure, temperature, and the materials used to construct these vessels. Submarines are built for high-pressure environments where the weight of water above creates immense forces pushing inward. On the other hand, spacecrafts must deal with the vacuum of space where there's no external pressure at all. In the deep ocean, water pressure can increase to 1100 psi at depths reached by nuclear submarines like the US Navy's Ohio-class vessels. This intense pressure is constantly pushing inward on the hull, forcing submarine engineers to use thick, durable materials like steel and titanium to prevent the vessel from being crushed. Conversely, in space, there's no atmospheric pressure, and the challenge is maintaining internal pressure without anything pushing back against the hull. While submarines are airtight and capable of maintaining an internal atmosphere, their hulls aren't designed to deal with the stress of internal pressure in a vacuum. How does the vacuum of space affect a submarine's hull? Submarines are built to resist compression, not expansion. In space, the lack of pressure could cause the hull to bucket outward if not properly reinforced, as it wasn't designed for outward stress. Spaceships, on the other hand, are constructed with materials specifically chosen to withstand the rigors of a pressureless environment. Submarines and spaceships also face vastly different challenges when it comes to temperature. Underwater, submarines operate in relatively stable temperature conditions with the cold ocean water surrounding them and acting as a natural coolant. In the deepest parts of the ocean, temperatures drop to near freezing, but submarines are insulated and rely on seawater to dissipate the heat generated by their nuclear reactors. Space presents an entirely different thermal challenge. Without an atmosphere to regulate temperatures, objects in space experience extreme fluctuations from scorching heat when exposed to direct sunlight to freezing cold when in the shadow of a planet. Could a submarine manage these temperature extremes in space? Without the cooling effects of water, a submarine would struggle to radiate excess heat. Nuclear-powered submarines generate immense heat, and without water to absorb it, the interior of the vessel would overheat dangerously. Can a submarine sustain life in space? One of the primary functions of both submarines and spaceships is to sustain human life in environments where oxygen isn't readily available. Submarines have sophisticated life support systems that produce oxygen by extracting it from seawater through a process called electrolysis. While this works well underwater, it raises a significant question. How would a submarine generate oxygen in the vacuum of space? Without water to process, a submarine's electrolysis system becomes useless. Although submarines carry backup oxygen supplies for emergencies, these reserves are only designed to last for a few days. In space, where missions can stretch for months or even years, this oxygen supply would run out quickly. In contrast, spaceships rely on closed-loop life support systems that recycle air and water using advanced filtration technology to provide astronauts with breathable air for extended periods. Submarines would need to be retrofitted with similar systems to function in space. Additionally, managing carbon dioxide levels is critical for long-term space missions. While submarines have CO2 scrubbing systems, they would need to be upgraded to handle the unique challenges of space travel, where every molecule of air must be carefully recycled. Moving a submarine in space presents significant challenges. Perhaps one of the biggest challenges in using a submarine as a spaceship is propulsion. Submarines move by using large propellers to push against water, a dense fluid that offers resistance. This method of propulsion works perfectly in the ocean, but in space, where there is no water or any other medium to push against, propellers would be completely ineffective. Spaceships, on the other hand, use rockets or other propulsion systems that expel gas or ionized particles to generate thrust. These systems don't require a medium to push against, making them ideal for space travel. A submarine could potentially be retrofitted with rockets to navigate space, but it would require significant redesign. Submarines aren't equipped to house rocket fuel or the necessary propulsion systems for space travel. Furthermore, the weight of a nuclear submarine, often over 10,000 tons, would make it difficult to launch into orbit, let alone maneuver in space. As a spacecraft re-enters Earth's atmosphere, it encounters immense friction, which generates heat levels exceeding 2,500 degrees Fahrenheit. Spacecraft are coated with heat-resisting materials designed to withstand this intense heat, but submarines lack such protection. Upon re-entry, the submarine's hull would likely melt or disintegrate, breaking apart long before reaching the surface. Spaceships are built using lightweight, heat-resistant materials designed to endure the stresses of space travel. Submarines, built to withstand the crushing forces of the ocean, use thick, heavy materials that are unsuitable for the high-speed re-entry process. Both vessels must create and maintain habitable environments for their crews, and the technology used to recycle air, remove carbon dioxide, and manage temperature is similar in some respects. For example, the International Space Station uses systems originally developed for submarines to filter and recycle air. Additionally, both submarines and spaceships rely on nuclear power for long-duration missions. The nuclear reactors used on submarines are similar in some ways to those that might be used on deep space missions where solar power isn't a viable option. However, while there is some overlap, the environments that submarines and spaceships operate in are so different that most of their technology is not interchangeable without major modifications. For instance, the propulsion systems, thermal controls, and materials used in spaceships are vastly different from those used in submarines, reflecting the unique challenges of space travel. The idea of a vehicle that can operate both underwater and in space has been a staple of science fiction for decades. Movies and books often depict hybrid vehicles capable of seamlessly transitioning between the depths of the ocean and the vastness of space. But is this idea purely fictional, or could it ever become reality? While current technology makes the concept of a submarine functioning as a spaceship highly impractical, advancements in material science, propulsion systems, and life support technology could eventually bridge the gap between these two environments. Future engineering breakthroughs could lead to the development of a hybrid vehicle capable of exploring both the deep sea and outer space. It's not impossible, but it would require overcoming significant technical challenges. Some companies and researchers are already exploring the possibility of dual environment vehicles. These projects, while still in the early stages, show that the idea of an underwater to space vehicle isn't entirely out of reach. However, for now, submarines and spaceships remain highly specialized vehicles, each designed for a specific set of challenges that the other cannot easily overcome. Ultimately, while the idea of using a submarine as a spaceship captivates the imagination, the significant differences between the environment of the deep ocean and outer space present too many insurmountable challenges for this to be feasible with current technology. Submarines are designed to survive crushing ocean pressures, while spaceships are engineered for the vacuum and radiation of space. These vessels may share some technologies, but their purposes and the environments they navigate are too distinct to make one easily adaptable over the other. However, this thought experiment sheds light on the intricate engineering behind both submarines and spacecraft. It reminds us that the specialized designs of these vessels, though different, are both marvels of human innovation. Who knows, with advancements in material science, propulsion, and energy storage, the future could bring vehicles capable of exploring both the deep ocean and the vastness of space. If you found this exploration into the world of submarines and spaceships fascinating, don't forget to hit the subscribe button and click the notification bell for more thought-provoking content on science, technology, and engineering. Leave a comment below with your thoughts, and let's keep the conversation going.